All right, so good morning, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. If you're joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. So last week was our first week back in 2021. We know it's a really odd year for all you teachers, just like 2020 was. So we really appreciate you all tuning in live and on YouTube as we continue to highlight such fantastic people and places from across the globe. So last week we did a lot of really cool animals. We had cool birds, we had baby sloths eating flowers, we had big cats and more. And today we are completely and utterly changing tack as part of our January STEM Careers Month. So we are joined live in Saskatchewan by Dr. Costa, and he's going to explain a little bit today about how you can use mathematical models to predict the future. So he's joined us before in this broadcast. He's a researcher at Environment and Climate Change Canada and the University of Saskatchewan. It's only our third, I think, Saskatchewan presentation, so it's really nice to have him joining us from there. And I can't wait to learn a little bit more about all the cool work he gets to do in, again, helping predict the future. So, Dr. Costa, thank you so much for joining us today, and take us away.
Thank you. Well, it's really great to be here. It's the second time, and it's always a pleasure to try to share my enthusiasm about this. And since you're at school, you're progressing in your mathematical skills. It's great that you get a glimpse of what you can do in the future as you progress, and the amazing things that scientists are doing nowadays. So really the objective here is to give you a journey through mathematical models and how scientists nowadays use them to try to predict the future. And I start with this image here of a Lake Winnipeg. And the reason is because it's just for you to, have an idea about how complex natural systems are. So if we want to try to model these things, it's complicated. It really needs a lot of team efforts and building on knowledge that has been, being developed over thousands of years, really. And so the first thing is really when you look at your phone, you look for the weather forecasts. There's no guessing. There are no crystal balls there, no magic potions or any of that sort. It's everything based on mathematics, on knowledge accumulated over the years, and the sweat and hard work of scientists around the world working together to get better and better at what they do. So when you say, well, the forecast was really bad, bear in mind that this is complicated and people are working very hard, and things are getting better by the day. So it all starts first grade, kindergarten. You start building getting the first building blocks of understanding counting, mathematics, and how to start putting things together. And then you graduate, you get more knowledge. And if you're interested in combining, for example, chemistry with physics, then you really need to have study the environment around you, not only the theory, but also observe. If you are earth scientists, you need to go out there and explore. Basically, you need to explore, observe, try to understand what things are doing and why. When you jump into a mathematical model, everything becomes abstract. So it's really critical that scientists understand what the models are doing, and they can compare with what they observe, and then they can progress towards. We actually have a very nice name for this. It's a model mimicry. Mimicry being mimicking reality, mimicking the environment. And then there's a lot of hard work, really a lot of hard work, many hours, and a lot of frustrations and overcoming challenges. And working together is really the critical point here. This is just an image of a cyber defense competition. It has nothing to do with earth sciences, but earth sciences nowadays, especially for prediction, they involve a lot of computer science. So you need to bring all of this expertise on physics, chemistry, computer science, and having all of these experts together to try to provide the best predictions possible. All right, so how earth scientists predict the future? Through mathematical models. But this is a big area, and I'll try to dig a little bit into that just to give a perspective of the things that our people currently do and the huge potential that these approaches and techniques have. So the first thing is really you study the world and then you collect evidence for natural processes. There are many PhD students, master students out there, some field scientists, others are more on the computer side, but you're just collecting evidence, trying to make sense of those things, and in some situations use the computers and models to also help further that understanding. And then you try to do model mimicry, as I said before. So creating these mathematical models and try to represent each of these processes inside the computer in a virtual world. So then you can try to simulate what is happening, and then you can try to project into the future. And the foundations for mathematical model can, from a long time. It's in the incremental progress for records of counting and writing numbers. So the need of using mathematics, trying to make sense of the world around us. There are records since 30,000 BC. But then it progressed over the years, of course, with astronomy, architecture. There are civilizations like the Babylon, Egypt, India that have a decent knowledge of mathematics a long time ago. And then it came more. That was probably with Pythagoras, where the study of pure mathematics started to actually becoming more substantiated and more formal, let's say. But then he went from there. Pythagoras, you probably or have studied trigonometry. So this is all probably very you're familiar with that. But then comes the theory of numbers. So trying to theorize a little bit mathematics and try to understand the potential that there is within understanding how numbers work. Okay, and I will not go through all of this, but this is just to tell you and give you a sense of that this is an incremental process that people have been building over many years. Okay. So what is a mathematical model? It's the very first question. A mathematical model is an expression that can represent a particular process. Okay, so let's say in this particular case, we're talking about the second law, the Newton's second law, which basically relates mass, so how heavy an object is, and multiplies by acceleration, and that will give you how much you need to push or pull this object. So this is really important, as you can imagine, for designing the engine of a car. You need to know, how heavy the car is, how fast you want it to go, how fast you want it to accelerate. So you need to, then you can, if you apply such a, this is a very simple equation, but just to give an idea, then you will know how much, how strong your engine will have to be. So as you can see, it's a very practical aspect to this example. Then this is another example. These are very simple examples, of course. This is the parabolic water or projectile motion trajectory. So if you will throw an object at a certain angle, you will make a certain pathway or a certain trajectory. And this is very well explained by this expression. And basically, just to walk you through this, it looks like if you are one of those that don't like mathematics, just try to forget all of that anxiety you have with mathematics. Just look very practically, in a very practical way, to this expression. It's basically you want to know where your object will be in this axis. So here, or here will give you a number. So you multiply by the velocity, let's say 5 meters per second, times the time. So I want 3 seconds after. So let's say here we'll start. I want 1, 2, 3. I want to know this particular point here, where it was here and here. So that's what is t here. So you just replace by 3, and then the cosine of the angle at which the object was thrown. So that's it. Voila! You have the x value here, the y position. So you can track where your object will be over space and time. Now, this is a very simplistic, very simple example. In the environment, things are a lot more complicated. So imagine, for example, you are in this particular example where you're throwing an object in the air. Well, you may have wind, and wind can vary over time in space. So things become very messy and very complicated. You couldn't really approach an Earth problem in such a simplistic way. you can't say in certain situations, but if you really want to simulate all the processes and dynamics, that very complex dynamics that occur over space and time, then you need to have something a little bit more robust. And that's where I want you to understand one particular set of equations that are really, really amazing and just revolutionize completely the Earth of environmental modeling, which is, I'll go to that in the next slide. So we want to simulate all this complexity. Such a simple expression cannot represent and mimicry all of these processes. This occurs at multiple scales. It's just multiple scales over space and time. There's a push and pull, and it's very chaotic. It's, for example, in the example of a river, it's highly dependent on where the rocks are, where the trees are, all of these dynamics of and the inertia, all of these processes going on. So it becomes extremely complicated with such a simple expression. And so that's where it comes what we call the partial differential equations. And you probably are looking at this expression saying, whoa, this is not for me. Yes, this is complicated to solve. This is requires a lot of computer power. But I want you to draw your attention to certain aspects of this. So this is just an example of what we call the Navier-Stokes equation. So this is basically representing in a mathematical way how fluids move in the environment. And this can be applied to rivers, can be applied to the atmosphere, is applied across many, many disciplines. But yeah, I want you to look into these expressions, to these equations, the Navier-Stokes equations, just as an example, and try to see if you see any pattern that is different from the typical expressions and equations that you are used to look at. I'll give you 3 seconds just so I don't throw the answer very quickly. I'll just give you 3 seconds. So the main difference between this type of equations, it has a particular pattern, and that particular pattern comes with what we call the derivatives. Okay, don't get scared with the name derivatives. It's just, if you look at this, you're going to see always d. This is a d something dt, d something dx, d something d. So there's a repetition here. dx, dy, dx, y. So x, y, and z, as you can see, it's the different dimensions, x, y, and z. So how it's moving around in the three-dimensional worlds. And t is time. So how is it moving over time? So what is now in 5 seconds, in the next 5 seconds, and the 5 seconds following, and on and on and on. So as you can see, all of these expressions which describe the movement of a fluid, they're all based on this particular aspect or particular approach technique called derivatives. So the x, dy. So what this is doing is very, very, very interesting and just changed completely the way we approach things. So you don't have any more, something on your right-hand side of your expression, you plug in whatever you want, and boom, voila, you have on the left side your answer. This is a little bit more complicated to solve, but just sets the ground for what we do now. So the first thing to look into when you look at these partial differential equations is that, okay, we want to model, let's say in this case, we want to model the entire world. We want to make a model for atmospheric dynamics across the entire world. Okay, that's it. So the first thing you have to do is basically to put a mesh or a grid around your world. Okay, you need to divide this in small squares. Okay, and within each square, you're going to say that everything that is below this falls on this area. All the terrain, the landscape, and vegetation, and so on and so forth, will have approximately or roughly the same characteristics. Okay, and so when you're modeling and you're solving those equations, you're going to solve for each of these squares, each of these points, which can be 1 million or 500,000 or 2 million cells. Okay, then you have over space or over depth. You can also subdivide these different layers in the atmosphere. So basically, you're creating a Lego, let's say, Lego construction, a very simplified or Minecraft kind of representation of your world. Okay. And then what you're going to do is basically go by cell, each of those cells, and you're going to solve those equations. So you have to solve all of those equations for all the points, all these points, this point, this in your domain. So this is now looking at the other, that's this example here, but looking in perspective, just to give an idea how your terrain could be. This could be a stream bed, okay? Just moving, the water will move this way, okay? So you're going to solve your equations for each of these points, okay? And you're going to do this over and over, all of those that you saw, it was like 5 or 4. You're going to solve for each of these points, you're going to solve once, and then you're going to solve over time, many times, okay? Why? So what do you do here? What you're actually doing, it's much simpler than you may think. What you're doing is saying, okay, I want to know, I cannot control the whole, I cannot have the one expression that's going to tell me exactly how water will be in this particular spot, because it's so complicated. But what I can do is to compute step by step, slowly. So what I do is that I just look, imagine I'm in this point. I'm going to calculate the difference, the change between this point to this point in terms of height of water. From this point, let's say I'm interested in this one, from this one to this, and from this and this one, difference between these two. So I have dx and dy. Okay, dx and dy. So I'm just going to calculate the differences, because the differences is really what you're going to drive your change. Let's say I'm here, I'm a water column. Look at me, I'm a water column. Next to me, I have another water column that's much higher than me. Obviously, through gravity, that water will move in my direction until there is an equilibrium. So we are more interested in the change instead of just the final result. So we do is just look at all of these changes, all of these differences, and see what is the potential of water coming into one direction, from another direction, and so on and so forth. Okay? So this is what we do, and we repeat this thousands, millions, sometimes billions of times, that we have to repeat this calculation and to really have a simulation over time. And that takes a toll computationally. It's very expensive computationally. But I can just give you an example here, because then we can, overlay other processes. So that one, the previous one, those very complicated equations that we call the Navier-Stokes equations, those represent or mimicry the movement of a fluid, or the fluid dynamics, what we call fluid dynamics. In this case, I want to know, all right, we know that, so this is what the water is doing. This is actually the simulation of solving those equations. You can see it's quite exciting. This is the terrain below. This is just a synthetic or hypothetical simulation, but you can see it's quite interesting because it can capture what you would perceive as a natural behavior of a fluid. And in this case, we can just then, overlay other processes. Let's say I have a contaminant being thrown at that water. Well, how is that contaminant going to move with the fluid? So we just overlay another set of equations. Again, the same type of pattern: dx, d something, dt, d something, dx, dy, dz, and on and on and on. Okay, and then you solve on top of that, and you have a beautiful representation of reality. And this is giving you an example of a simulation from our lab in Jakarta. And so this is a flood event, just to give you an idea of how all of these equations can then be applied to real world problems. So this is looking at how a flood moves through the center of Jakarta in Indonesia, and how contaminants, so this is an hypothetical contaminant, how it would spread over the city and in the floodplains, and on and on. So it has very practical and a huge potential, as you can imagine, for solving real world problems. Well, this requires a lot of power, a lot of computational power, and that's the reason you've been seeing and you've been hearing over the years, the more computational power. You have this supercomputer, you have that supercomputer. It's really because of what I just explained. You have to solve those equations for each of those squares that you saw, and you have to solve it for now, and then for predicting the position of the water in 5 seconds, and then the 5 seconds after, and on and on and on. So you have to solve that thousands, millions of times, depending on how long you want the simulation to go. Weather forecast is the same thing. You want to predict for within a week, for tomorrow. So these computers are simulating these processes in cycles all the time. So when you look at your phone, you look at the weather forecast, you know this was a computer simulation. It's been going on, it's been running over and over and over and over again, okay? So this is just an example of one high-performance computer called Graham that I use personally very frequently. But there are dozens, if not hundreds, of computers, supercomputers available out there, and it's much easier to access them than it used to be in the past. This is just to give you flops. It's just a measure of how much supercomputer can calculate, how many processes it can calculate or tasks. And of course, as you can see, it's been a spectacular increase in computational power. But I hope that with what I presented before, you understand why the need for this, because you don't have simple equations that you can solve. You have to get with these very complicated equations that they don't really give you the final answer. They give you rates of change, and then those rates of change will help you go from one place to the other, from today for tomorrow, and so on. So you have to calculate all of those steps along the way. And just to conclude, I want to give you I wanted just to show you. This morning I accessed Graham, which is a supercomputer, and just to give an idea of how easy it is to access these computers nowadays. We just log in, we get inside, we make our simulations, and we get our results. That's it. It used to be, you used to need, you'd make requests, wait for your time, then you'd have to have these punch cards. This is not during my time, for sure, of course, but nowadays it's as simple as this. You ask for protocol, you give your name, your account name, I want to go to Graham. This is within the clusters of computecana.ca. Boom, you're there. You just put your password. You're inside the supercomputer. It's as simple as this, and then you can ask him to do the simulations you need it to do. So it's very easy nowadays, and it has a huge potential. So how earth scientists predict the future has nothing to do with this. It has to do with this. It has to do a lot with hard work, and then people getting together every year in science meetings. This is an example of the American Geophysical Union. Probably it's the biggest geophysical, the biggest conference for earth sciences in the world, where everyone goes for a week. We learn what other people are doing. We have these poster sessions. We can interact with each other, and we can see what others have accomplished, how they progressed, and then that's how science evolves. And yes, so just to finalize, if you're interested in having a look at some of the work we do, and just feel free to go to this website. But there are terrific scientists around the world where you can see what they are doing, and really across many disciplines, not only in earth sciences, in engineering, in medicine, you name it. This is really has a huge potential for helping solving the problems of our age. Thank you.
Thank you, Dr. Costa. And so let's dive in with Q&A, folks. We've got at least 4 groups joining us on YouTube from across Ontario and Alabama. So welcome into our teachers and homeschoolers there. 6 groups live with us in the broadcast from all across the province of Ontario. So welcome in, over 200 kids tuning into this broadcast. So nice to have you guys all here. For our teachers that are live, if you'd like to type to me in the chat bar, if you have questions, I will come to you on that basis. I'm going to start with some of my own and take some from YouTube as well, and we will dive in. So Dr. Costa, my first question is, because this is STEM Careers Month, what sort of education do you need? What sort of background do you need to get a job like yours? What was your journey, and how would one of our students watching today end up with a career like yours?
Well, it's well, I did civil engineering, but you can actually apply these models across many disciplines. It's just more the love for mathematics, and then have love for science. If in the case of earth sciences, wanting to explore and trying to understand the world around you, and if you have a love for computer sciences or computers in general, it's just a great way also to give a purpose to that passion, to try to solve the problems of the environment nowadays. It's a great challenge, really.
Fantastic. Well, speaking of solving those problems and making those models, Mr. Mayo's class joining us in Ontario, they want to know how accurate are these models. So we're building this up. We have better computers. We have more people working on it. how can we be sure that they're good, they're effective?
Well, there are many ways of testing the performance of a model. There are many metrics. It's basically what you do to assess if your model is accurate is to make measurements in the field. So in the case of river flows, there are river gauges across the entire country, and they record the flows, and then you first validate your model. So you build your model. So this, for example, the Navier-Stokes equation is really well established. It's been used for many years. But then, when you apply the model, then you see the predictions, you compare against observations, and you say, okay, it says this capacity of prediction, and then after you do that process, that's when you look into the future and you have some confidence on your result, on the prediction capacity of the model.
Awesome. So we got a question from Ms. Arkeen's class, grade 4s in Toronto, and Ganesh wants to know, how can they predict the weather in another city? So I want to speak to the fact that this is an international enterprise. How many other researchers around the world are doing this sort of work? Like, how are we collecting this data? Where are people located doing the sort of things that you're doing?
Well, I think it's mostly universities and federal research agencies. There are more people working on this than you may imagine. This is, for example, in Canada, it's the National Hydrology Research Center as a huge computational component to it, but it also runs radars for the case of weather forecast, which is not actually my field. But you have, over many years, so you have field scientists who actually are more into measuring in the field. So they are these are teams that go and collect samples. For example, in terms of chemistry, just to give a completely different example. So just go regularly to streams. They take samples, they take them to the lab, and they measure nitrate, phosphate, whatever you name it, all this chemistry, and then field scientists, biogeochemists, they will look into that data. And then we have people like me and others who will try to look at that data and try to build models for those data. So the idea is always to, if you think this way, for us to really answer the urgent questions of the environment nowadays, you need to look at big scales. For example, Lake Erie has been suffering eutrophication for many years. Many of you are from that area, and it's a huge problem. It's very difficult. The watershed is huge. It has agriculture. The land is farmed. There's a lot of nutrients being run off through those landscapes. It's very difficult. So you can imagine it's huge. There's so much heterogeneity, and there's also the fact that the farmers will apply the fertilizer and they will not tell us that they apply that fertilizer. So it gives a lot of uncertainty. So, but you need these people in the field measuring, observing what the farmers are doing, and then people like me come and try to model these things with uncertainty. Of course, there's uncertainty.
Well, so speaking of this uncertainty, the Pizzatelli family joining in Vancouver, they wanted to know, we'll get to that question in a minute. Sorry, I take that back. Wrong question. Mr. Mayo's class, what happens when they're wrong? Like when these calculations are wrong, you predict how floods are going to, impact Jakarta. You're highlighting this stuff. What sort of real world results does that lead to?
Well, that's the danger of trying to predict the future, right? It's a very challenging proposition, right? A dangerous one. So I think the most important thing is to communicate correctly. So when we're saying that this is predicted, people have to bear in mind this is based on these computer models. That's why I thought it was very important to have this talk, just for you to know that this is based on this. It's based on mathematics. It has a lot of uncertainty. But it's very valuable and has shown in the past that can do amazing things. But it needs to be used with caution, and we need to have be aware of that. Okay, so this is a prediction. We don't know for sure what's going to happen until it happens, right? But this is the best prediction we can have. It's not based on crystal balls or anything like that. It's based on science, what we know about the processes. We know a lot about those processes, and so we bundle them together in these computer models, and we do our best, as a prediction. That's why the weather forecast, it's not always accurate, right? But people are working on those things to make them more and more accurate as time goes.
Well, this is the thing, and this actually speaks to that question I was going to share a minute ago from the Pizzatelli family, which is How is sharing this information worldwide? How is this global collaborative effort, these big conferences that you highlighted with all these researchers from around the world, affected how accurately you can predict things?
Oh, for sure, they are critical. I mean, it's we are in our own bubble. Although the world is very connected, for us to build a model like this, it's a lot of work. You probably it takes sometimes it can take years to build the model that can solve those equations accurately. Or there's a lot of field science of field science field, science fields that are related to solving those equations. You have the numerics, you have the mathematics, and then you have the actual physical world, the hydrology, the geography. So that's where these conferences are critical, because we need to get together. So we get so close in our bubble trying to solve our huge task, in front of us to solve those equations accurately. Then we have to open a little bit, look at the big picture, see what other people are doing, discuss. Then these conferences are also great because we can then discuss future projects and identify issues, problems that we can further improve our models. So they are really important to help the connection. Although we all publish in journals, scientific journals, it's like drinking from a fire hose. It's so much, and the quality is also can vary, right? So you don't really know sometimes how valuable that contribution is. So you need to dig through all of that, and you also have your work to do. So it's all of a management of time, and these conferences tend to be really important for people to communicate and actually see where science is moving.
Yeah, there's a great follow-up question on this, Hamilton, and they wanted to know, prior to COVID, how many times a year did you gather and meet with engineers like yourself to discuss these predictions and patterns?
It's actually interesting because it's for example, if you have a PhD scholarship, it's within that pot of money that will be to pay your salary. There is usually also money for conferences. So just for you to have an idea how important that is, and that usually, so let's say a PhD program is 4 to 4 years. Usually you have it varies, of course, but usually you can go at least to one conference per year, 1 to 2. I go to 1 to maximum 3. Because it also takes time, right? And then you have to prepare the material, and then you have to go there physically. At least pre-COVID, right? You have to go physically. So there's a benefit, but it also takes time. So you need to manage that. But it's important that you go every year and see what's happening in your field and discuss with your peers. This is also a very important aspect. It's your peers. Acknowledge your peers. They are making progress as well. And sometimes with completely different perspectives, and they might not agree with the way you do things. And you might not agree with the way they do things, but it's important that you keep going to their talks to try to understand their world and see why they're doing through that perspective, and not avoiding the clash. Science is about consensus. So the science is not about this is the answer. You have one paper, that's it. This is the answer. It's not like that. It's about consensus in the sense that I publish a paper pointing that this is the best way of developing these models. Let's say other people come and they do things slightly different. Others say, oh no, my way it's better, and the other ones try another method, and they come to another conclusion. And over time, the best approaches, or the ones that work the best, were more efficient for many ways, or were more practical to apply. That's also another question. Will tend to elevate towards with respect to the others who will be more used. So this is how it works, with consensus, not just imposing things. It's a very organic process.
Yeah. Excellent answer, and great question, guys. All right, Ms. Patel's class in Toronto, they want to know how long were you personally interested in computer science, and how much training, how long in training did it take you to reach this position?
Well, in my case, it took a while because I did my undergraduate. I'm Portuguese, so I did my undergraduate in Portugal, and then at the time, I was not very interested in pursuing a scientific career. But then it was when I had the opportunity to work with a professor as a research assistant that that world opened to me, and I just got really, really excited about that. So there will be this time where you get excited, and then one thing that I may recommend is just to, if you're really interested in that, it's to set a plan. Think about the next steps, and that's what I did. I knew I had to do at least a master's to try to elevate myself in terms of background, in terms of credentials, let's say. And then from there I applied to PhD programs, and I was accepted, and then then you went from there, and so this is then the PhD, and then the PhD you still need to do a postdoc nowadays. It's very difficult to go from a PhD to a postdoc. So we're talking about quite a few years between university, 4 years, then you have a master's, 2 years, 6 plus 4. We're talking about 10 years, including the university degree, right? And then you have the.
Well, I love highlighting this because it sounds so daunting and scary. If you're a grade 4, if you're going to grade 12,
Yeah.
spending 10 years past that, but that means you're about 28, and now you're equipped to do a career that is really fulfilling and exciting and high paying and allows you to travel and do all these things that you want to do, which 28 might seem like ancient right now. It's my age for some of our students. It really does set you up in a really nice position to do a lot of fantastic.
And I also like to add that when you are a PhD student or a master, sometimes you are paid. So you're not in some cases you might not have a scholarship, but in most cases you'll have a scholarship. So you are being paid to do the government, the federal government, or whatever the funding agency is, are giving you money for you to do some research, but also to elevate your education. So don't and even if you, and then the next step will be a postdoc, some 3 to 4 years or 2 years, it depends. You are also being paid, right? So you're being paid to do something that you enjoy.
The best of all possible worlds. We're going to take a few more questions, guys. These have been great pouring in. So our Rainbow Virtual School team in Sudbury, they want to know, how far in advance can we get prior warning of extreme weather events with models like this, like tornadoes or hurricanes? And I'd also recommend to the school that in a couple hours, we've got a program on hurricane modeling and a hurricane thing. So if you want to check that out too, it'll be on YouTube. But Dr. Costa, if you have something to speak to this, please do.
Yeah, I'm not a weather specialist. The models I developed are focused on river dynamics and contaminant dynamics. But one thing that you have to bear in mind is that these type of models, based on these partial differential equations, so these differences, so they the more you go over time, if you're looking at forecasts, so looking to the future for weather, the more you try to predict, the further away, the more inaccurate it will be. There's more uncertainty going on, right? There is, in terms of weather, we have turbulence, we have eddies forming, and there are lots of local processes that are difficult to model. So that's why there's still a lot to improve in the models. Yeah. But of course, you have to bear in mind that this is, as you said, we are covering, in the case of the weather forecast, we are covering the world in this mesh. So each of these cells will have, we're going to consider in the model that they have uniform conditions in terms of landscape, everything. So it's an approximation, right? But hopefully the idea is that it's an approximation that is useful, that gives a useful prediction.
Yeah.
Okay.
Excellent. And again, for our students, if you do want to hear from weather experts on that sort of modeling, come back in an hour and a bit. But thank you guys for that question. All right, I'm going to take one last one from one of our live classes, Mr. Shattuck's class, joining in Chalk River, Ontario. You mentioned Minecraft earlier, Dr. Costa, and so they want to know, would modeling for water like we've seen today be useful for video game programmers?
Yes, that actually, I remember a while ago that there was a group of it was a company, and they wanted to have in their animations, they wanted to have fluids moving around, and they resorted to the Navier-Stokes in a simplified way. So you can simplify that equation, but they actually use that Navier-Stokes equations to have a realistic. In their case, it's not about being accurate. It's more being realistic, and they actually use those principles. So I'm sure that software companies and game developers, they are very in tune to these developments for sure.
Scientists get to play a role in movies, video games, all in that regard nowadays. It's another cool perk. If you're excited to become a modeler, there's lots of things you can do. One last thing I want to mention, and there's been variations of this question both in our chat bar and on YouTube. We've had a lot of kids asking about the modeling in terms of predicting global warming or climate change. Is climate change real? And so I want to make a personal statement here for all our students tuning in, just as an effort to combat misinformation. Climate change is real. We've known the science for many, many decades now. It's a scientific consensus around the world. Every major scientific organization confirms this. We can see it with our own eyes now, which is, not a good thing, but something that really drives the point home. So we really want to stress climate change is real. Environment and Climate Change Canada is an entire department in the government of Canada committed to understanding, showcasing this work. So I just want to make that point for all our classes tuning in today. And I do appreciate the questions from our curious students. We want to make that very, very clear for everybody. Dr. Costa, is there any last message you want to wrap up the broadcast with? This has been so great.
Yes, I mean, just don't get the long pathway that takes to get to these careers. To encourage you, it's have fun along the way. Get excited. That's why I think it's important to look outside and see how the process is. You see with your own eyes. Actually, outside it's full of snow now, so it's good to see how things are working and be curious. And then if you have a passion for gaming and for computers, you just bringing the two worlds together. It's great.
Well, thank you so much. Again, I think that's a lovely message to leave our kids with, and it's such a pleasure not only having you in, but again, continuing our series with Environment and Climate Change Canada. So exciting, featuring scientists from all across the country. So I really appreciate your time with us today, Dr. Costa.
Thank you for having me, Jess.